Alright, so regarding the motor, this is what I have figured out. The impedance of phase A, is 28.4 millihenries. The impedance of phase B is 28.8 millihenries, and C is 28.7 millihenries. From phase to phase, A to C, we'd have 57.1 millihenries. And in ohms, that's 6.2 ohms, basically, for all three phases. Diameter of the wire is 0.7 millimeters. The capacitance of each phase is 2 nanofarads. Okay? The capacitive reactance for this motor is 7.957 kiloohms. That's this CR. That's capacitive reactance, 7.957 kiloohms. The LR is inductive. L stands for induction. That's inductive reactance at 3.587 kiloohms. And the impedance is 12.5 to 14,370. Okay. Here's the commutation sequence that it needs to go in. There are 12 steps to the sequence. There's actually 24 steps to the sequence, but there are 72 steps to the sequence. Anyways, here are the measurements for here's your numbers for your inherent resonant frequency is 10 kilohertz. So that's very important to understand. The inherent natural resonant frequency of the motor itself with these specifications is 10 kilohertz. And the capacitance is 2 nanofarads. The inductance is 28.4 millihenries. And the resistance is 6 ohms. So your controller needs to be based around those numbers right there. And the capacitive reactance, 7.95 kiloohms. The inductive reactance is 1.78 kiloohms. And the impedance is 6 ohms. With a resonant frequency of 21.117 kilohertz. The stator has 36 poles, 12 poles for each phase. It's only firing from one phase to another at any given time. So at any given time, you only have 24 poles that are active. And you have 24 magnets, 24 poles, 12 north, 12 south. Each phase must switch 24 times per revolution, times 3 phases is 72 cycles per revolution. Okay. This chart, or these notes, describe what is impedance. Impedance, the total measure of opposition to electrical current, and is the complex vector sum of real resistance and imaginary reactance. That's what impedance is. Okay, impedance, or impedances, which are represented by the letter Z, the capital letter Z, are managed just like resistances, which are labeled R, capital R, in series circuit analysis. Series impedances add to form the total impedance. All calculations in complex form, not scalar. Z is the total equals Z1 plus Z2, blah, blah, blah. Purely resistive impedance will always have a phase angle of exactly 0. Purely capacitive impedance will always have a phase angle of minus 90 degrees. And there's your formula. When resistors and capacitors are mixed together in circuits, the total impedance will have a phase angle between 0 and minus 90 degrees. A purely inductive impedance will always have a phase angle of plus 90 degrees. When resistors and inductors are mixed together in circuits, the total impedance will have a phase angle between 0 and plus 90. The circuit current will have a phase angle somewhere between 0 and minus 90. And that's what we're dealing with the motor. We're mixing resistors, inductors, because the stator, each phase is an inductor, and we're mixing capacitors, capacitance, with the resistors. So these phase angle calculations are all important to understand. Series resistor capacitor circuit voltages lag by 0 to 90 degrees. Pure inductor current lags voltage by 90 degrees, and that's important to understand too. And those pictures don't really mean nothing. So here's your 6-step sequence. T1 is transistor 1, and you can see that it is on for a period of 120 degrees. That's what that chart means. All these numbers at the bottom, 60, 120, 180, 243, 360. Those are all your phase angles. So transistor 1 turns on at 0 degrees, and it turns off at 120 degrees. And it turns off for a period of 60 degrees. And it turns, and then transistor 4 kicks on at 180 degrees, and then kicks off at 300, and and then there's a dead space to 360. So, however, during this first cycle, during this first 120 degrees, you can see that T1, T6, and T2 are all turned on at the same time. Well, T2 doesn't turn on until 60 degrees, but T1 and T6 both turn on at the same time until 120 degrees. Well, until 60 degrees, and then T6 turns off, and then T2 turns on. And then at 120 degrees, T2 stays on, T3 comes on, T1 turns off, and it stays, T2 and T3 stay on till 180 degrees. And T2 turns off, T3 stays on, T4 comes on until 240 degrees, and then T3 turns off, T5 turns on till 300 degrees, then T4 turns off, and then T5 stays on, T6 comes on till 360 degrees, and it starts over. And that's per cycle, per 360 degrees of rotation of the motor. And here's how your three-phase bridge rectifier would be connected. You have T1, top left, T2 on the opposite corner on the bottom, T3 top middle, T4 bottom left, T5 top right, T6 bottom middle. That's how they're labeled. T1 and 4 make phase A, T3 and T6 make phase B, T5 and T2 make phase C. As long as you follow that labeling, you'll be correct. And there's how it connects to the motor. This is the symbol for the motor. There's your A phase, B phase, C phase. See, as A phase is turned on, it goes from 1, transistor 1, flows through your first winding, out your second winding, and to your T6. Phase 1, T1 to T6. Look up here, T1, T6, for your first 60 degrees. Okay? 0 to 60 degrees is T1 to T6. It's your visualization for it. It's from A to B. There's your first sequence. And then your second sequence is A to C, bam to bam, 60 to 120 degrees. And then on down the line. Okay? That's how you understand that. So the gate pulse, the duty cycle for each phase is 33.34 degrees. Because think about it. You're dealing with 360 degrees, and you're dividing it into 3 phases, 3 sections. When you set your duty cycle to 33.3 degrees or percent, you end up with a 120 degree phase differential or topology. So there's your resonant frequency, 21.1 kilohertz. That would mean your wavelength is 14,000 meters, blah blah blah. That's just some calculations for something else. So if you look at a 50% duty cycle, 4 squares would equal 1 whole cycle, or 360 degrees. 50% means it's on half the time, off the other half. But a 33% is only on for 30% and then off for the rest of the time, 75%. So you would have your 1, 2, 3 phases all in one complete rotation. And it makes a waveform that looks similar to that on the scope. It's a double helix. And actually it's a little more complicated than that, because there's a third wave hidden within those two waves. There's a third wave. This is pretty self-explanatory if you just go through and read that and that. Then when it gets to the schematic, there are basically two sections to, well, there's actually three. Well, there's two sections to the controller, there's three sections to the whole system. You got your actual motor, your mechanical side of the system. You've got your power supply section, which steps up your normal 120, 240 volts, all the way up to 1200 volts DC. This is the circuit to not only step up, but to convert your AC to DC, so that you can provide your inverter circuit with DC power. Right here at the top, where there's this little plus, you can see that it comes down and connects to that capacitor over there. That is the symbol for a capacitor. That's the symbol for a diode. And then you have a transformer, step-up transformer. And then you're also stepping up the voltage with this multiplier circuit. This is a voltage multiplier circuit right here in the middle, coming out of the transformer. And it also converts the AC to DC to provide your link, which will switch your DC voltage, your high DC voltage, and deliver it to the motor in the proper order. Now these transistors have three connections. The top, the little connection coming out the side, and then the little connection coming out the bottom, which goes to the motor and to this other transistor. The little wire connect, all of the little ones that go over here, that's the low voltage side, which go to these gate drivers. This GD1, that's gate driver 1. And that's an electrical component that's kind of computerized. Anyways, and your controller is what holds your sequence, and it's what it delivers a low voltage signal to your gate drivers, which step up that low voltage signal to a little bit higher voltage, but still low, and it feeds the signal to the high voltage transistors. These gate drivers have protection built in so that high voltage doesn't feed back. That's basically their purpose. And off your main 120 volt power supply, you can also come off to another step down transformer, which will step you down to 12 volts AC, and then you can rectify that into DC with a little smoothing capacitor in there, and feed that to run your low voltage side. So you can run everything off of one source, step your voltage down to run your electronics, step your voltage up to run your inverter assembly And that's basically all it is. There's a control side, which is low voltage. There's your high voltage side of your power supply. And then there's the power inverter section, which will deliver your high voltage pulses to the motor, which is controlled by the computer. So if you want to use a general program that exists out there on the market, you want to look for this SVPWM. That's called Space Vector Pulse Width Modulation. And you want to be able to set it to 12 poles. It'll do the math already. You want to set it for a max frequency of 21.1 kilohertz for an RPM of 3,600 RPMs. So that's basically the explanation in a nutshell. Any other questions? Just let me know. Peace.